An ohmic conductor is a conductor that obeys Ohm's law. In other words, in that conductor, the potential difference is directly proportional to the current strength, provided that the temperature remains constant. But there are factors that influence the resistance in a conductor. So even your normal little conductor offers a measure of resistance. I'm not talking about the resistor now, I'm talking about the wire. So the first thing is the type of material. You get really good conductors, and those good conductors have low resistance. Funnily enough, some of your best conductors, unfortunately, are gold and silver, but they are too expensive. I mean, we have cable theft as it is. Can you imagine what it would be like if our cables were gold? So we don't really use gold. So the best, cheapest, cost-effective version for type of material is copper, which unfortunately, as we know, does sometimes get subjected to redistribution and cable theft, but it is not as expensive as some of the even better conductors. Right, then the length of the conductor makes a difference in the resistance of the conductor. The longer the conductor, the higher the resistance. Now, I don't know if you've ever noticed, perhaps with charging your phone, if you have a really, really long cable, your phone doesn't charge as effectively or as quickly. That is because that longer cable offers higher resistance, so it can't charge as well. So yes, where extension cords are good, using too long extension cords can actually influence the resistance of the circuit and thus the functioning of the circuit. Right, a thick conductor is better. The thicker the conductor, the lower the resistance. If you think of it, if we had a giant big tunnel to pass through, a whole bunch of us could pass through at the same time, so lower resistance. Whereas we had a teeny tiny little tunnel, we would have to pass through 1, 1, 1, 1, 1, and that would increase the resistance. And the last one is the temperature of the conductor. Remember, Ohm's law specifically mentions that it happens at a constant temperature, because what happens, the hotter the temperature, the higher the resistance. Now, I want you to just think about life here. On those super hot sunny days, when you've been lying in the sun, you feel very, very lethargic. So you have a high resistance to carry on with life. Okay, we also feel a bit that way when it's too cold. We want a perfect ambient temperature. And so do our conductors. Right, now onto what is actually classified as matric work. But let's make sure that we super duper duper understand it from grade 10. If we look at a battery, there is a chemical reaction taking place in that battery. Now, I'm sure you've experienced a leaky battery before where like some of the liquid comes out, or maybe you've even seen it in a car battery before where there's liquid that comes out of it. A chemical, that is because of the chemical reaction that is taking place in the cell, in the battery. Now, I'm sure you remember from right now when we did bond energy, a chemical reaction requires a certain amount of energy to take place. Now, that energy that it uses, we talk about as the lost volts. And it is used to overcome the internal resistance of the reaction taking place in the cell. So now we need to make sure we understand this. The total potential difference of the cell is known as the EMF, and it is the value given to us when the circuit is open. Ironically, that is generally the number that they print on the battery as well. So you think, oh, wow, it's a 1.volt battery. And then you put it in a circuit and it only provides you with 1.3. Marketing people. So the voltmeter, when I have an open circuit, in other words, my switch is open, my circuit isn't flowing, there's no current in the circuit, will give me my EMF. Just by the way, if I put a voltmeter over a resistor, or if I put an ammeter in the circuit, the voltmeter over the resistor is going to read 0 volts. The ammeter is going to read 0 amperes when the switch is open. But the voltmeter over the battery will read the EMF. That is the maximum energy output. However, when you close the switch, turn on the circuit, the voltmeter reading drops. And that is now the actual potential difference that is being delivered to the circuit. The difference between the two is known as the lost volts. So the EMF is equal to the volts plus the lost volts. And the lost volts are the volts that go into the battery to make the reaction take place, to overcome the internal resistance. Right, please remember, lost volts and internal resistance are not the same thing. The lost volts, measured in volts, is used to overcome the internal resistance, measured in ohms. So if we look at the equations, the first straightforward equation that we know, R is equal to V over I. The big R is the resistors in the circuit, the V is the potential difference given out to the circuit, and the I is the current. If we look at the internal resistance, that's the baba R, like a R, and it's equal to the lost volts divided by the current. Now, if we combine those two equations, so the big R plus the little r, the V plus the lost volts, we get the EMF. And that is where the equation EMF is equal to I, big R, plus little r comes from. It's a combination of a little internal resistance equation and a big resistor equation. Right, let's look at a quick example. Here it gives you just a simple series circuit, and it says calculate A, V1 and V2. So maybe if you want to try this by yourself quickly, pause the video, do the sum, and then let's check your answers because they're coming up right now. So the first thing we would need to do is we'd need to add the resistors to get the total resistance. Always an equation. RT is equal to R1 plus R2 plus R3. So 3 plus 4 plus 6 is 13 ohms. And it's a good idea, grade 11s, even when you're practicing, write the equation. Because if it becomes a habit to write the equation, you're not going to make a silly mistake under pressure in a test or an exam and forget the equation to lose the marks. Then we'd use the EMF equation in order to get the current. So EMF is equal to IR plus R. So we know the EMF is 12, it's given. The current's what we're looking for. 13 plus 1 for the internal resistance would be the resistance, the R plus little r. So if we do the maths, that's 12 divided by 14 is I, and therefore I is 0.86 amperes. Series, so current is the same everywhere. Now to work out the two little voltmeters. So if we are looking at a voltmeter or a specific resistor, it's almost like make a big circle around it on your picture so that you know you are dealing just with it. So voltmeter 1, we are just dealing with the 4 ohm resistor. So we'd say R is V over I, 4 is V over 0.86 because the current is the same everywhere. And we get that the voltmeter reading V1 is 3.43 volts. For V2, again, we'd say R is equal to V over I. Now we are just dealing with the 6 ohm resistor. So it's V over 0.86, and it gives us 5.14 volts. The secret to do electricity is do as many examples as possible, as only so many things can be asked. Maybe the numbers can change, the picture can change, but the method stays the same. And now is the perfect time during lockdown to do lots and lots and lots of examples. Even repeating examples and looking through your grade 10 book for extra examples will help. If you're not sure what to do, break it down into bite-sized chunks. Design a little flow diagram for yourself in order to get from one point to the next. Then just a teeny bit of new work, but it's not a lot of work, is power is the rate of electrical energy conversion in a circuit. It is measured in watts. So look in your textbook for the examples. They're on page 360 and 361. Complete exercise 20, number 2, 3, and 4 on power. And then also have a look at the cost of electricity on page 368 to 370. Now, cost of electricity, it is something you did in grade 9, and it's not something they really ask about in matric, but just have a look at it and make sure that you get the basics of it. Power, what they do is they'll usually give you a circuit and ask you questions about the resistors or the combined resistors or the ammeter reading here, there, and everywhere. And at the end, they'll say, so what is the power through the circuit? And you'll see, if you look on your information sheet again, you'll see there's a whole bunch of power equations. They're all related to the original one, where power is the rate of work done, so W over delta T. And from that, they get P is VI, P is I squared R, or P is V squared over R. So depending on what you have, calculate the power. Then the exam questions at the end of the chapter, or the end of the whole book, it's actually on page 379 to page 396. The last two questions, though, on page 398 and 400 have graphs, which I'll spend time teaching you in class because it's absolutely imperative you do understand these graphs. Now, none of these questions have EMF. I'm going to send you some examples on EMF, but I would like you still to complete all the examples on page 379 to 396. It's very good practice. And then, like I said before, especially if you struggle a little bit with electricity, exercise 19 on page 355 is really not a bad idea of things to do. Really, electricity shouldn't be a difficult section for you. It should be something that you want to do. It's quick and easy. And now's a great time to practice getting it right. So I will be sending you further examples with EMF and past paper, even grade 11 ones without EMF, so that you can practice it. One last thing. Remember, if they say internal resistance is negligible, that word negligible means that it is zero. So in other words, that cell doesn't have internal resistance. We're not working with EMF and internal resistance. We are working with just Ohm's law. R is equal to V over I. I trust you've learned something from this current electricity video, and I hope you have a great day and that you stay safe and stay healthy. Be blessed.